सो आज हम लोग जो है बेसिकली अपना मोड चेंज करने वाले हैं। ठीक है, हिंदी भाषा से इंग्लिश भाषा की ओर। ठीक है, इसके पीछे रीज़न है, वन ऑफ माई सब्सक्राइबर इज फ्रॉम southern part of India. Basically, he requested me to make videos in uh, basically English mode, so that he would be also be comfortable with the concepts. All right. So today concept we are going to discuss is age hardening. Or it is also popularly called as precipitation hardening. Now the question, very first question comes to my mind is that why another method of hardening came into picture? Since there were too many methods of hardening like work hardening, case hardening, why age hardening? It can be asked in your interviews. So the answer to this question is, when you study anything, first ask why we are studying. Like why we are studying thermo, why we are studying FM, why we are studying material science. Alright, so why age hardening? Answer is simple, that other methods were for steel and other alloys, but in this method we are talking especially about non-ferrous alloys, right? Like aluminum copper alloy, aluminum magnesium alloy. This alloy is very popular in market as duralumin. We have seen the wings of aircrafts. These wings of aircrafts are manufactured from duralumin, and also the gas turbine blades are manufactured from this duralumin also. So it's a general information which you must keep in mind, and also this information you should also keep in your mind that 5.5% of copper is present in aluminum, in duralumin, right? So especially we are concerned about this aluminum copper phase diagram. Okay, so why this PPT has been why this name has been kept Professor Wilm? Because this phenomena was observed by the great Professor Wilm, who was he was from European nations. I don't know the exact where he was from. So this phase is liquid phase, this phase is alpha phase, this phase is alpha plus liquid phase, and this phase is alpha plus Al2Cu phase. Basically, 2 moles copper is combining with 2 moles of aluminum, and along with this intermetallic compound, the ferrite phase is also present beyond this line. This phase mixture is stable. Okay, एक मिनट right. So and so sorry, there is mistake here. No, basically liquid phase is beyond this, so don't confuse in that. Basically, liquid phase is beyond this. So what Professor Will did, he took the sample at room temperature and heated till this point. Why he heated till this point? Why not heat one to this point? Because this is a mushy region. Alpha plus liquid region is present, and we want that no mushy region and pure alpha should be present in the microstructure or grains, right? So he didn't cross this line, and after reaching to this point, he quenched it to back to its room temperature. And what he was observed that copper gets basically when he quenched back. So our common sense or common whatever we have studied till now, that beyond this line, there should be a phase mixture of alpha plus aluminum copper, right? But Professor Wilm was shocked to see that there is no Al2Cu. Now he was shocked that only alpha phase is present within the grains. So he started thinking and he was disturbed and he threw the sample. And it was a time of Christmas. And in European countries, 2 months of holidays are for Christmas, right? So he threw the sample, and coincidentally, he visited his rooftop. He threw it to his uh, rooftop, and coincidentally, after 2 months, he visited again. He visited to his rooftop, and again tested the hardness of the sample. Now he found that hardness was increased. How this? How come this phenomena is possible? How come this phenomena is possible that before 2 months there was no change in hardness, and after 2 months there is sudden change in hardness? So he was shocked. Now again he did the same experiment and repeated. He took the same sample and heated till a temperature where pure alpha phase is present and quenched back to the room temperature. Again, same situation arrived that no change in phase, no Al2Cu was found. But so he was confused why this happens. But after lifting the sample, after lifting the sample for 2 months, there was hardness, change in hardness. But when I quenching, when I heat treating it, I am doing heat treatment to room temperature, there is no change in, there is only alpha phase is present. So some conclusion was drawn that due to quenching, this copper which is present in aluminum is not combining with 2 moles of aluminum. It is being freed at its position, freezed due to rapid quenching, sudden quenching. Copper is like it is in shock. What has happened? Sudden quenching. Sudden quenching is rapid cooling. Copper did not understand what has happened to me. He not even moved from its position. Okay. So when he left the sample for 2 months, then copper realized, oh, something has happened to me. Now copper start diffusing because copper has to combine with 2 moles of aluminum. In the same aluminum was present all around it. Now when copper realized that I have to combine with 2 moles of aluminum because I have crossed this boundary. Now Al2Cu, I have to form this compound. Now when it formed the compound, now hardness of the sample has increased, and basically how hardness has been increased, this you must understand this, that this Al2Cu compound is present in the grains in the form of precipitates, small precipitates, right? And whenever these precipitates are a basically obstruct causing are barrier, basically they are barrier in movement of dislocations, right? So whenever there is a barrier, there is increase in stress. We have to apply more and more stress uh, in order to change the size of the sample. This we have studied in work hard, obviously. So due to precipitation, so small precipitates, it acts as a barrier in the moment of dislocation. So strength increase due to this reason. So when you will see, when I will observe this graph, you will find this, sorry, strength versus time. You will find that strength was increased, strength versus time graph, until this point. After that, strength started falling down. Why this strength has fallen down? This process is called overaging. When when we left again for some time, these precipitates now combining and form a bigger compound. And these big compounds are now repelling each other and creating a space. Now dislocation is seen that there is space between two, and now dislocation moment is bit easier compared to the previous one, right? So now dislocation is, now it is an easy for dislocation to move compared to early situation. Although it is also difficult, but it's not so difficult compared to the previous situation, right? So strength has started decreasing compared to the previous situation. This is process is called overaging, right? Okay. Now basically we have quenched it to room temperature. Now if you quenched it to temperature greater than room temperature, obviously what will happen due to increase, what I am telling that, what I am trying to say, that we are quenching it to, we are quenching it to room temperature. This is the room temperature. Oh, 1 minute please. Now when we are quenching it to room temperature, it was taking a long time. 2 months of time is bit longer time. And in industrial application, obviously this will not work at all, because production time is a big factor, right? We are manufacturing aircraft wings, so we have to increase the temperature from room temperature to some other temperature, T2, T, it is T1, it is T0. So now we are, what we are doing, that we are increasing temperature to T2, right? So what will happen due to increase in temperature? Diffusion will increase, and due to, because diffusion is a function of temperature, and due to increase in diffusion, now more and more precipitates will form, and when more and more precipitates will form, the graph will shift towards right, left. This peak was observed at very lesser time, and now why the strength has decreased compared to the early situation. Basically, in earlier situation where temperature was room temperature, suppose 100 moles of precipitate was formed. Now when we have increased it to room temperature, now 70 moles are only formed. Due to lesser number of moles, these precipitates will bit larger in size compared to the previous situation. So this is the reason why strength has decreased, because now the dislocation can easily move compared to the previous situation. We are quenching it to room temperature, now we are quenching it to T2 temperature. So precipitate size will be more larger as compared to the previous. So This is the reason why strength has decreased, but the time has also decreased compared to the previous one. In previous situation, this was the time and peak was over. Now, only this time we get the maxima. Okay.